Hello, everyone. Today, we're diving into Chapter 17, Radioactivity and Nuclear Chemistry. This topic isn't just for physicists. It has critical applications in healthcare. You'll learn how radiation helps us detect diseases, treat cancer, and understand how nuclear reactions power medical imaging. Let's begin with why this matters in nursing practice. Radioactivity plays a vital role in nuclear medicine. For example, when imaging the thyroid or bones, radioactive substances allow us to see inside the body clearly and non-invasively. As future nurses, understanding the basics of how this works will help you comprehend procedures involving PET scans or isotope imaging. Here's an NCLEX tip. You may encounter questions about the safety precautions for handling radioactive materials or patient instructions after a scan using radioactive isotopes. In nuclear medicine, tagged antibodies seek out infection. If a patient has appendicitis, these antibodies will collect in the inflamed appendix. The radiation they emit shows up on imaging film, guiding physicians in diagnosis. Connection to nursing. You'll often be responsible for explaining these tests to patients or managing their care afterward, including isolation precautions if radioactivity is involved. Here's an NCLEX practice question. A patient undergoes a diagnostic scan using radioactive antibodies. Which of the following nursing instructions is most important? A. Encourage the patient to drink fluids. B. Keep the patient NPO. C. Administer antibiotics before the scan. D. Avoid moving the patient for 24 hours. The correct answer is A. Encourage fluids to flush out radioactive materials. Radioactivity refers to the release of tiny particles from unstable atoms. These particles carry energy and can affect living tissue, which is why they are so useful and sometimes dangerous in medicine. Analogy: think of unstable atoms as popcorn kernels under heat. Eventually, they pop and release energy. In 1896, Becquerel discovered that uranium salts could expose photographic plates even without sunlight. This told him something invisible and powerful, radiation, was being emitted from the uranium. Connection to nursing. This was the foundation of medical imaging. Understanding this helps you explain how diagnostic tools like bone scans and thyroid scans work. Becquerel initially thought the exposure came from light, but he later realized that the uranium was always emitting something, what he called uranic rays. These rays turned out to be radiation. Remember, radiation does not require an external trigger. It's spontaneous and constant in radioactive materials. Marie Curie built on Becquerel's work and asked, do other elements emit radiation too? She discovered polonium and radium, two highly radioactive elements. NCLEX connection. You'll hear of radium therapy in cancer treatment history. Curie's discoveries laid the groundwork for radiation therapy. Radium was so radioactive that it glowed and gave off heat. It was once used in luminous watch dials. Unfortunately, this led to many cases of radiation sickness before the risks were fully known. Safety tip: always treat radiation with respect and use proper protection. Even seemingly small exposures can be dangerous over time. Marie Curie was the first person to win Nobel Prizes in two different sciences, physics and chemistry. Her work is still relevant today, especially in radiation therapy for cancer. Inspiration for nurses. Curie worked tirelessly in field hospitals during World War I using X-ray technology to help soldiers. She was not just a scientist, but a healthcare pioneer. Curium element 96 was named after Curie. Her daughter Irene also became a Nobel Prize-winning nuclear physicist. This family helped establish the foundations of radiation use in medicine. Reflective point: as a nurse, you're part of a legacy of healthcare professionals who use scientific discoveries to save lives. Let's talk about the different types of radiation. While Curie was focused on discovering new radioactive elements, scientists like Ernest Rutherford were asking a different question. What exactly are these emissions coming out of radioactive atoms? They discovered that radiation comes from the nucleus, the central part of an atom, and that atoms emit different types of particles to become more stable. These emissions are how atoms get rid of excess energy. There are three major types we're going to focus on: alpha particles, beta particles, and gamma rays. Each one has different properties, different strengths, and different effects on the body, which is especially important for us in healthcare. Now, not all atoms are stable. Some are just too big, or they have an unbalanced ratio of neutrons to protons. That's when they start emitting radiation. We call this radioactive decay. When atoms decay, they might release alpha, beta, or gamma radiation. Smaller atoms usually need a 1-to-1 ratio of neutrons to protons to be stable. But bigger atoms, like uranium, need more neutrons than protons to hold the nucleus together. Understanding that balance helps us predict which atoms are likely to be radioactive. In healthcare, this matters because different types of radiation have different risks and uses. For example, a substance used in a PET scan will emit a different type of radiation than something used in cancer therapy. NCLEX style review. Which type of radiation has the highest ionizing power but the lowest penetrating power? That would be alpha particles. We'll talk more about that in a minute. You might have seen symbols like this in your textbook, something like uranium-238 written with two numbers, one on top and one on the bottom. The top number is the mass number. That's the total number of protons and neutrons. The bottom number is the atomic number, just the number of protons. This is called isotope notation, and it's a helpful way to represent different forms of the same element. Isotopes have the same number of protons but different numbers of neutrons. And some isotopes are radioactive. Those are the ones we use in nuclear medicine. In nursing, you'll hear about radioactive isotopes like technetium-99m, which is used for bone scans, or iodine-131, which is used for thyroid conditions. You don't need to memorize all the symbols, but you should recognize how to read them and know that isotopes are often used in diagnostics and treatment. Let's start with alpha radiation. Alpha particles are made of 2 protons and 2 neutrons. Basically, they're like a tiny helium nucleus. When an atom emits an alpha particle, it loses both mass and protons, which actually turns it into a completely different element. For example, when uranium undergoes alpha decay, it turns into thorium. So this isn't just a chemical reaction where atoms rearrange. This is nuclear chemistry. The atom literally transforms into something new. In medicine, alpha radiation isn't usually used for imaging because it doesn't travel far. But that doesn't mean it's harmless. Alpha particles have very high ionizing power, which means they can do a lot of damage if they get inside the body. That's why alpha emitters are dangerous if inhaled or swallowed, even though they can't even penetrate skin. When radioactive decay happens, we write something called a nuclear equation to show what's going on inside the atom. It's similar to a chemical equation, but it tracks changes in the nucleus, specifically the number of protons and neutrons. Here's the key point. The total mass number and the total atomic number must be the same on both sides of the equation. Just like with money, you have to account for everything that goes in and out. Let's say we start with uranium-238 and it gives off an alpha particle. We subtract 2 protons and 2 neutrons. That leaves us with thorium-234. We're not just changing mass here, we're changing the identity of the element. In nuclear chemistry, we use the word nuclide to refer to a specific type of nucleus. The original atom is called the parent nuclide, and the new atom it turns into is called the daughter nuclide. Remember, unlike regular chemical reactions where the elements stay the same, nuclear reactions often create new elements. That's a big deal. You're literally changing the building blocks of matter. This is important for understanding things like radioactive decay chains, where one radioactive element decays into another, which might also be radioactive, and so on. So again, when we write nuclear equations, we have to make sure everything is balanced. The mass number and the atomic number on the left side of the equation must equal the total on the right side. This is just like balancing a budget or a medication calculation. You need to account for everything to make sure the math checks out. And just like in your NCLEX dosage questions, if something doesn't add up, you've probably made a mistake. In nuclear chemistry, that could mean identifying the wrong element. Let's walk through how to write a nuclear equation for alpha decay. Suppose you start with thorium-232. It emits an alpha particle. That's 4 on top and 2 on the bottom. So subtract 4 from the mass number and 2 from the atomic number. That gives you a new element with a mass number of 228 and an atomic number of 88. Now look on the periodic table. What's element 88? That's radium. So your daughter nuclide is radium-228. And now your equation is balanced. This type of deduction is useful if you're working with radiation therapy or handling isotopes in a clinical setting. We just did an example where thorium-232 undergoes alpha decay to become radium-228. This is the kind of transformation we see in natural radioactive decay chains. One element becomes another, which might decay again. These sequences help scientists understand radiation exposure and help healthcare professionals know how long a substance remains dangerous in the body. Quick NCLEX-style check-in. If a radioactive substance emits alpha particles, what's the main safety concern? It's not external exposure. It's internal exposure, like inhalation or ingestion. That's where alpha radiation becomes truly dangerous. So what makes radiation dangerous? It comes down to ionizing power and penetrating power. Ionizing power is the ability of radiation to knock electrons off of molecules. When that happens inside the body, it can damage DNA or other critical structures in the cell. Penetrating power is how far the radiation can travel through matter. For radiation to harm internal organs, it has to be able to get past skin and tissue layers. Alpha particles have very high ionizing power, but low penetrating power. They can't get through skin. Beta particles are smaller and can go deeper. Gamma rays, on the other hand, have very high penetrating power. They can go through the body and even some shielding, but they don't ionize as much. Understanding these two properties is key for setting up radiation protection protocols for patients and staff. Let's talk more specifically about alpha particles and how they affect the body. Imagine an alpha particle as the semi-truck of radiation. It's huge compared to other particles. Because it's so big, it crashes into things very easily, and that means it can do a lot of damage to molecules it hits. That's called high ionizing power. But here's the catch. Because it's so big, it also gets stopped really easily. A sheet of paper, your clothing, even the air is usually enough to block alpha particles. That means they have low penetrating power. So if alpha radiation is outside the body, it's not a big concern. But, and this is important, if alpha emitters get inside the body, maybe by breathing in contaminated dust or drinking contaminated water, they can do serious harm. That's why we take so many precautions when handling radioactive substances in healthcare. As nurses, you'll need to understand which types of radiation require external shielding and which ones are more dangerous if they enter the body. Now let's move on to beta particles. Beta radiation happens when a neutron in the nucleus turns into a proton and an electron gets ejected. That ejected electron is the beta particle. So now the atom has one more proton. It becomes a new element. Unlike alpha particles, beta particles are much smaller and lighter. They don't crash into things as easily, so they don't ionize as strongly, but they can travel farther into the body. Beta radiation has moderate ionizing power and moderate penetrating power. It can go through skin, but can usually be stopped by a metal sheet or thick plastic. In medical settings, you might see beta emitters used in things like eye plaques to treat eye cancer. Nurses need to know how to protect patients and themselves appropriately based on the type of radiation being used. On a nuclear equation, a beta particle looks like this. 0 on top, -1 on the bottom. Why? Because it has essentially no mass compared to a nucleus and it carries a negative charge, just like an electron. When an atom emits a beta particle, the atomic number increases by 1 since we've gained a proton. But the mass number doesn't change much because we're just swapping out a neutron for a proton. You might see this symbol in questions about radioactive decay or even in interpreting isotope scans. Let's do an example. If radium-228 undergoes beta decay, what happens? A neutron in the nucleus turns into a proton and a beta particle electron is emitted. That means the new atom now has one more proton. Its atomic number increases by 1. The mass stays the same. So now radium-228 becomes actinium-228. This equation needs to be balanced, just like we talked about before. The total mass numbers and total atomic numbers on both sides must match. And remember, this is how new elements are formed in radioactive decay chains. So how dangerous are beta particles? If alpha particles are like semi-trucks, then beta particles are more like compact cars, smaller, faster, and able to maneuver into tighter spaces. Beta particles don't cause as much ionization as alpha particles, but they can penetrate deeper into tissue. That makes them more dangerous when they're outside the body compared to alpha particles. A beta emitter on the skin can do more damage than an alpha emitter, but inside the body, beta particles do less damage than alpha particles because they don't hit as hard. So again, it's all about context. Nurses need to know not just what kind of radiation a patient is exposed to, but how they're exposed. NCLEX style tip. If a patient receives treatment with a beta-emitting isotope, appropriate shielding may include acrylic or plastic rather than lead, since beta particles can generate secondary X-rays when they hit metal. Now gamma rays are in a league of their own. They're not particles like alpha or beta. They're a form of high-energy electromagnetic radiation. Think of them like supercharged X-rays. Gamma rays often get released alongside alpha or beta particles. They don't change the atom's identity, but they do help the atom shed excess energy after a decay. These rays have no mass and no charge. That means they can travel long distances and penetrate deep into the body and even through it. In medicine, gamma rays are both helpful and hazardous. They're used in radiation therapy to kill cancer cells, but also require serious shielding. If we go back to our vehicle analogy, gamma rays are like motorcycles. They're fast, nimble, and can get through tight places. Gamma rays have high penetrating power. They can pass through skin, tissue, even bone. But because they're not particles, they don't ionize as much. They don't hit hard, but they go far. To protect patients and staff, gamma radiation requires thick shielding. We're talking several inches of lead or concrete. In radiology, nurses should know when shielding is needed and how long a patient may be radioactive after a scan or treatment. NCLEX check-in. A patient has just received a gamma-emitting isotope. Which precaution is most important? The answer is usually time, distance, and shielding. Limit exposure time. Stay a safe distance away and use shielding when needed. Here's a cool one, positron emission. It's kind of like beta decay, but in reverse. Instead of a neutron turning into a proton turns into a neutron, and the atom emits a positron, a particle with the same mass as an electron but a positive charge. This type of decay is used in PET scans, which are very common in detecting cancer and monitoring metabolic activity in the body. So what happens to the atom? It loses a proton, meaning the atomic number decreases by 1, and it becomes a different element. In nuclear equations, a positron is written with a 0 on top and a +1 on the bottom because it has almost no mass but a positive charge. Positron emission is often paired with annihilation radiation. That's when the positron collides with an electron and they destroy each other, releasing gamma rays. That's actually how PET scanners pick up the signal. For nurses, this means being aware that patients receiving PET scans have a temporary radioactive signature. Depending on the isotope used, you may need to follow precautions for radiation safety. So in summary, positron emission is similar to beta decay in how it affects mass and atomic number. But instead of adding a proton, it subtracts one. It has moderate ionizing and penetrating power, not as strong as alpha or gamma, but still enough to be useful and require safety protocols. In the hospital, you'll see positron emitters in oncology and neurology. These isotopes help us see active tissues, especially in the brain and cancerous tumors. Understanding how this works empowers you to explain it to your patients, answer their questions, and ensure everyone stays safe. Let's pause here and summarize what we've learned so far about radiation types. Alpha particles are big and heavy, 2 protons and 2 neutrons. Because they're massive, they have high ionizing power, meaning they can damage a lot if they hit something, but they also have low penetrating power. They can't even get through your skin. That's why they're only dangerous if they get inside your body. Beta particles are electrons emitted when a neutron becomes a proton. They're lighter, have moderate ionizing power, and moderate penetrating ability. They can get through skin, but not bone. They can be stopped by plastic or metal shielding. Positrons are like beta particles, but positively charged. They come from a proton turning into a neutron. These are the guys used in PET scans. And gamma rays, they're the heavy hitters when it comes to penetration. No mass, no charge, but very high penetrating power. They can go through tissue, bone, and even lead if it's thin. But they don't ionize as much as the particles do. So in healthcare, knowing what kind of radiation you're working with helps determine how we protect ourselves and our patients, what kind of shielding we use, and how close or long we can be near someone receiving radiation. This table visualized the 5 types of radioactive decay with examples. Now let's talk about how we detect radiation. One simple but effective tool is called a film badge dosimeter. This is a little badge with photographic film inside. Healthcare workers who work around radiation, like in radiology or oncology, often wear these. As radiation hits the film, it darkens just like when taking a photo. After a week or a month, the film is processed to see how much exposure occurred. The darker the film, the more radiation exposure you had. So if you're ever working in an area where patients receive radioactive treatments, or if you go into the room during a nuclear scan, you might be required to wear one of these badges. It's a passive way to monitor long-term exposure. Another way to detect radiation is using a Geiger counter. You've probably seen it in movies. It's the thing that clicks faster and faster as you get closer to something radioactive. Here's how it works. It has a chamber filled with argon gas. When radiation passes through, it ionizes the argon atoms, basically knocking off electrons. These charged particles create a tiny electric current, which is converted into either a meter reading or that clicking sound we all associate with radiation. In healthcare, this is more commonly used in labs or industrial settings, but the key takeaway is this: radiation can't be seen or felt, but we can measure it with the right tools. Now let's look at another radiation detection tool, the scintillation counter. This one works a little differently. When radioactive emissions pass through certain materials like sodium iodide, NaI, or cesium iodide, CSI, those materials emit light. That's called scintillation. The machine detects the light, converts it into an electrical signal, and gives a reading of radiation intensity. Scintillation counters are often used in hospitals during scans and treatments to monitor exposure in real time. They can also help ensure that radiation therapy is being delivered accurately. As a nurse, your role might include checking these readings or making sure protocols are followed if the machine gives an alert. Here's something surprising. We are all constantly exposed to radiation. Even if you've never had a scan or worked in a hospital, radiation is around you every day. This is called background radiation. It comes from three main sources: radioactive materials in the earth and rocks, especially uranium, cosmic radiation from space, yes, even the sun, and radioactive elements in the food and water we consume. So don't worry, our bodies have evolved to tolerate low levels of radiation. The key concern in healthcare is extra exposure, things like CT scans, PET scans, or radiation therapy. In nursing, we always weigh the benefit against the risk. A properly performed scan or treatment gives us much more good than harm, as long as safety procedures are followed. Now let's talk about one of the most important ideas in nuclear chemistry: half-life. Half-life is the time it takes for half of a radioactive substance to decay. That means it turns into something else and is no longer radioactive. Let's say we start with 100 atoms of a radioactive isotope. After one half-life, we'll have 50 left. After two half-lives, we're down to 25. After 3, 12.5. It doesn't go all the way to zero quickly, it tapers off gradually. That's why we sometimes still detect traces of radiation thousands of years later. Why is this important in nursing? Because the half-life tells us how long a patient may be radioactive after a scan or treatment. If a patient receives iodine 131, which has a half-life of 8 days, they may need to take precautions for a couple of weeks to avoid exposing others. This graph shows what we just talked about. Imagine we start with 1 million atoms of thorium-232. With each half-life, 14 billion years in this case, we lose half of what's left. So, after 14 billion years, we have 500,000 atoms. After 28,250,000 remain. And so on. While thorium isn't used clinically, other isotopes with shorter half-lives, like technetium or iodine, are very important in patient care. You might be asked on NCLEX to explain when a patient is no longer radioactive. Half-life helps you answer that. Not all radioactive substances decay at the same speed. Some isotopes decay in minutes, others take billions of years. For example, thorium-232 half-life equals 14 billion years. Radon-220 half-life equals 1 minute. This has a huge impact in healthcare. We use short half-life isotopes in medicine so the radiation doesn't linger too long in the body. For example, technetium-99m is used in bone scans and only lasts 6 hours. Safe, fast, and effective. So the next time you hear a patient worry about being radioactive, you can confidently explain, "Don't worry, it fades very quickly." Here's a table listing various radioactive nuclides and their half-lives. Every nuclide has its own unique half-life, and here's a key fact. These half-lives don't change. They aren't affected by temperature, pressure, or anything else. That's what makes them so useful for both medicine and dating ancient objects. In nursing, the most relevant ones are the short-lived isotopes like technetium-99 in 6 hours, iodine-131 8 days, phosphorus-32 14 days. You may see these used in diagnostic imaging, thyroid treatment, or tumor detection. Knowing how long they stay active helps you manage patient instructions, like avoiding close contact with others, especially children or pregnant women. Here's something fascinating. Some radioactive elements don't just decay once, they go through an entire series of decay steps until they become stable. Let's take uranium-238 as an example. It's the heaviest naturally occurring element, and it's radioactive. Uranium-238 goes through multiple transformations. First, it decays into thorium-234, then to protactinium-234, then to uranium-234, and so on, eventually turning into lead-206, which is stable and no longer radioactive. Each of these steps might involve alpha or beta emissions, and each one has its own half-life, some lasting billions of years, others just days. This series is important because we still have lots of uranium in the environment, and that means we also have these other daughter nuclides floating around, some of which are more radioactive or more dangerous than the original uranium. This diagram shows the full decay chain from uranium-238 all the way to lead-206. You can see how many steps it takes and why even small amounts of uranium in the ground can lead to many different radioactive elements being present in the soil or air. From a nursing perspective, this helps explain why radon is a concern in homes. It's one of the intermediate products in this decay chain. Even if the uranium is buried deep underground, the radon gas it produces can seep into basements and become a health risk, especially for lung cancer. Let's zoom in on radon, since it's the most important health-related isotope from this decay series. Radon is a radioactive gas, and it's produced naturally when uranium decays underground. The problem is radon gas can seep into homes, especially basements. It has no color, no smell, no taste, but it's radioactive, and it can attach to dust particles that we inhale. Once it gets into the lungs, it continues to decay and release radiation inside your lung tissue, increasing your risk of lung cancer. In fact, radon is the second leading cause of lung cancer after smoking. For nurses, especially those in public health, understanding radon's risk is key to promoting home testing and ventilation systems in high radon areas. NSELECT style question: what is the most important instruction for a patient with high radon levels in their home? Correct answer: install a ventilation system or increase air circulation. This map shows the U.S. divided into zones based on radon exposure risk. Zone 1 areas, shown in red, have the highest natural radon levels. If you live in one of these red counties, the risk of exposure is higher, especially in homes with poor ventilation. Homes built over uranium-rich soil, like parts of Colorado or Pennsylvania, are especially vulnerable. As healthcare providers, we need to be aware of these regional risks. If you work in home health or family nursing, part of your role might include educating families on radon testing, especially if they have young children or immunocompromised individuals. Now we shift gears a bit. Let's talk about how radioactivity helps us tell time, really long time. Radiocarbon dating is a method scientists use to estimate the age of fossils, bones, or artifacts made from once living materials. The key is an isotope called carbon-14. Carbon-14 is radioactive, and it's present in the atmosphere thanks to cosmic rays interacting with nitrogen. Plants take in carbon-14 through photosynthesis. Animals eat the plants and so on. It's in all living organisms. But the moment something dies, whether it's a tree or a person, it stops taking in carbon-14. From that point on, the carbon-14 begins to decay at a known rate. By measuring how much is left in a sample, scientists can calculate how long ago the organism died. Pretty amazing, right? Here's how the cycle works. Cosmic rays hit nitrogen atoms in the atmosphere, converting them into carbon-14. That carbon gets turned into carbon dioxide and is absorbed by plants, which are then eaten by animals and then eventually by us. As long as something is alive, it keeps replenishing its carbon-14. But once it dies, the amount of carbon-14 starts to go down, and we can use that drop to figure out the age of the material. This doesn't have direct medical applications, but it's a powerful example of how understanding radioactive decay and half-life helps scientists and sometimes forensic experts draw important conclusions. Now, once the organism dies, carbon-14 begins to decay to nitrogen-14, and the half-life of this process is about 5,715 years. So, if a sample has half as much carbon-14 as living tissue, it's about 5,715 years old. If it has a quarter, then it's been dead for 11,430 years, and so on. Even though you won't use this in bedside nursing, understanding half-life decay will help you answer NCLEX questions about things like radioisotopes used in patient scans. Let's do a quick mental practice. If a piece of ancient wood has only 25% of the carbon-14 that's found in living wood, how old is it? Well, 25% means 2 half-lives have passed. And since each half-life is 5,715 years, the wood must be about 11,430 years old. Again, this is just one more way we use the consistent behavior of radioactive decay to measure time in science. And in healthcare, we apply this same concept to how long isotopes remain active in the body. All right, now let's talk about nuclear fission, splitting atoms to release energy. In the 1930s, Italian physicist Enrico Fermi bombarded uranium atoms with neutrons. His goal? To create new elements? He thought maybe by adding a neutron, uranium would become unstable and emit a beta particle, turning into an entirely new element. What he didn't realize at the time was that something much bigger was happening. The uranium atom was splitting, a process called fission, and releasing huge amounts of energy. This discovery would lead to both nuclear power and eventually the atomic bomb. Here are 2 names you should know. Enrico Fermi, who helped initiate fission research. The element fermium was named after him. Lisa Meitner, a brilliant physicist who helped explain how fission worked even though she wasn't credited at first. The element meitnerium honors her contribution. These scientists unlocked the secret of how breaking apart a uranium atom can release tremendous energy. This would later become the foundation for both nuclear medicine and radiation therapy. In healthcare, fission is how we generate the radioactive isotopes used in treatments. In public health, it's also how we manage the risks from nuclear power plants or radiation exposure. Let's go back to the 1930s. After Fermi's neutron experiments, 3 scientists, Lise Meitner, Otto Hahn, and Fritz Strassmann, repeated those tests and did something crucial. They chemically analyzed the results. To their surprise, they didn't find heavier elements. Instead, they found lighter ones like barium. That meant something amazing had happened. The uranium nucleus had split in 2. This was the first confirmed discovery of nuclear fission, breaking an atom apart and releasing energy. And that energy? It's immense. Much more than you get from any chemical reaction. That's the same energy that powers nuclear reactors and atomic bombs. And in medicine, it's the process used to generate radioactive isotopes for treatments and scans. In January 1939, Meitner and her colleagues published the first report of nuclear fission. This was a game changer for science. Here's how it works. A neutron is absorbed by a large nucleus like uranium-235. That makes the nucleus unstable. It stretches, vibrates, and finally splits apart. This fission process releases huge amounts of energy, produces smaller atoms like barium and krypton, releases more neutrons which can go on to split more atoms. This chain reaction is the foundation for nuclear power and radiation therapy. Let's focus on uranium for a moment. In nature, uranium comes in 2 main types. Uranium-238, which is stable and doesn't undergo fission. Uranium-235, which can undergo fission, but it makes up less than 1% of natural uranium. So if you want to use uranium to produce energy or medical isotopes, you have to enrich it, meaning you increase the percentage of U-235. This is how nuclear reactors and medical isotope facilities work. Once U-235 absorbs a neutron and splits, it releases three more neutrons, which can each cause more fissions. This is called a chain reaction, and it's how we generate a lot of energy very quickly. In medicine, small-scale reactions are used in facilities to create short-lived isotopes like those used in PET scans or radiation treatments. Here's what a chain reaction looks like. One uranium atom splits and releases three neutrons. If each of those neutrons hits another uranium atom, now you have three more fissions and 9 neutrons and so on. This reaction can either be controlled, like in a nuclear reactor, where energy is released slowly and used to make electricity or medical isotopes, or uncontrolled, like in an atomic bomb, where the reaction happens all at once and releases a massive explosion. In the medical world, we rely on controlled fission to generate the isotopes we inject into patients for scans and treatment. This is where the science became serious history. Once scientists realized uranium-235 could sustain a chain reaction, they also realized it could be used to make a powerful bomb. This led to the Manhattan Project, a secret U.S. government effort to build the atomic bomb before Nazi Germany could. Physicists warned President Roosevelt in a letter signed by Albert Einstein, saying it might be possible to build a bomb powerful enough to destroy an entire city. In healthcare, we don't use this for destruction, but the same principles that made the bomb possible are also behind cancer-fighting radiation and diagnostic nuclear medicine. The Manhattan Project officially began in 1941. Led by Robert Oppenheimer, it brought together thousands of scientists to secretly build the first atomic bomb. On July 16, 1945, the first bomb was successfully tested in New Mexico. A few weeks later, atomic bombs were dropped on Hiroshima and Nagasaki, leading to Japan's surrender and the end of World War II. Combined, the bombs killed about 200,000 people. Why are we learning this in a healthcare course? Because it's critical to understand the origin and power of nuclear energy. The same technology that caused devastation also gave rise to life-saving tools, like radiation therapy, nuclear imaging, and radioisotope treatments. And it's why nurses must treat radiation with deep respect and caution. Here's a photo from the first ever nuclear bomb test known as the Trinity test in 1945. That flash of light and shockwave you see? That's nuclear fission, atoms splitting and releasing energy on a massive scale. Again, in medicine we scale this way down, but the same principles apply. Controlled radiation can be used to diagnose disease, kill cancer cells, and even sterilize equipment. But it also shows us why strict protocols and protective measures are so important in healthcare when working around radiation. Now let's shift from weapons to something more peaceful: nuclear power. Nuclear reactors use the fission of uranium to generate heat. That heat is used to boil water, which creates steam, and the steam turns a turbine that generates electricity. Here's the key idea. Nuclear power plants produce a lot of electricity with very little fuel and without burning fossil fuels. That's why some see it as a cleaner alternative to coal or gas. In medicine, the very same reactors are used to create radioactive isotopes that are shipped to hospitals. In a nuclear power plant, the fission reaction happens in a reactor core. The heat is carried away by water in separate sealed pipes, so the radioactive water never touches the clean water used to make steam. This design protects workers and the environment from contamination. Understanding this helps us as nurses explain to patients that medical isotopes, like those used in thyroid scans or bone imaging, are safe when used properly and made in controlled, secure environments. Let's break it down a bit more. Inside the reactor core, you have fuel rods made of enriched uranium, U-235, control rods which absorb neutrons. When the control rods are inserted into the core, they absorb the neutrons and slow down or stop the chain reaction. When they're pulled out, the reaction speeds up and produces more heat. This system lets us control the fission process safely. It's kind of like using a brake pedal and gas pedal in a car. In healthcare, the radioactive materials made in these reactors are often packed into small sealed forms that are safe to inject or place near tumors for therapy. Now let's talk about what can go wrong when nuclear fission isn't properly controlled. In 1986, the Chernobyl disaster happened in the former Soviet Union. Operators at the power plant were performing an unsafe experiment and disabled several safety features. This caused the reactor core to overheat. What made things worse? The core was made of graphite, which caught fire. The fire then released radioactive material into the air for days. 31 people died immediately. But the long-term health impacts, especially radiation-related cancers, affected thousands more. So why does this matter to us in healthcare? Because many patients exposed to radiation, whether from an accident or treatment, need monitoring, protective isolation, and long-term cancer screening. And as nurses, we need to be educated about the risks of uncontrolled exposure. Now fast forward to 2011 in Japan. A 9.0 earthquake triggered a tsunami that flooded the Fukushima Daiichi nuclear power plant. The cooling pumps failed. Without cooling, the reactors overheated, and at least one experienced a partial meltdown, meaning the fuel rods got so hot they started to melt. Although the radiation release was significant, it was lower than Chernobyl, and thanks to better emergency systems, no radiation-related deaths have been reported. Even so, the cleanup will take years. As nurses, this teaches us how natural disasters can turn into radiation emergencies and why public health systems must be ready with evacuation, decontamination, and long-term monitoring protocols. Now let's talk about one of the biggest challenges of nuclear energy, waste disposal. Nuclear power doesn't produce smoke or CO2, but it does leave behind radioactive waste, and that waste can remain radioactive for thousands of years. Right now, in the U.S., we store this waste on site at the nuclear plants because a permanent solution like Yucca Mountain in Nevada was shut down in 2010. So what does this mean for healthcare? It means we need to be aware of environmental radiation risks. People who live near storage facilities or transport routes may have elevated exposure in the case of a leak. And for patients receiving radioactive treatments, waste handling, even like contaminated bedding or bodily fluids, must follow strict disposal protocols. Now let's shift from fission to fusion. Fusion is what powers the sun and stars. It happens when two small nuclei like hydrogen atoms combine to form a bigger nucleus like helium. This releases even more energy than fission. Here's the reaction you often see in textbooks. Hydrogen plus hydrogen, helium plus energy. Sounds great. Now let's shift from fission to fusion. Fusion is what powers the sun and stars. It happens when two small nuclei like hydrogen atoms combine to form a bigger nucleus like helium. This releases even more energy than fission. Here's the reaction you often see in textbooks. Hydrogen 2 plus hydrogen 3 form helium and energy. Sounds great, right? So why don't we use fusion in power plants? The problem is it requires extremely high temperatures, millions of degrees. At that level, no material on Earth can contain the reaction safely except for short bursts in experimental reactors or bombs. Fusion is also the process behind the hydrogen bomb, which is 1,000 times more powerful than the atomic bomb. Fusion has been studied for decades as a cleaner alternative to fission because it produces less radioactive waste. But again, the challenge is temperature. Fusion needs plasma, a superhot gas where atoms are stripped of their electrons. And to contain that, we need magnetic confinement or inertial compression, which are both complex and expensive. So while it's an exciting area of research, we're not there yet. For nurses, this may sound abstract, but it's relevant because many medical isotopes are created using fusion-like reactions in research labs. And understanding fusion helps build scientific literacy about energy, radiation, and safety. Now let's talk about how radiation affects the body. Acute radiation damage happens when someone is exposed to a large dose of radiation all at once, like during a nuclear accident or bomb. The most vulnerable cells are the ones that divide quickly, like those in your immune system, bone marrow. Intestinal lining symptoms include nausea, vomiting, hair loss, immune suppression, difficulty absorbing nutrients. In mild cases, patients may recover over time. In severe cases, especially without treatment, death from infection or organ failure can occur. As nurses, we must know how to recognize signs of radiation sickness, provide supportive care, and follow decontamination procedures. Even lower doses of radiation, if received over time, can cause DNA damage, increasing the risk of cancer. Normally, when a cell's DNA is damaged, the cell either repairs itself or dies. But sometimes the damaged cell survives and grows out of control. This is how cancer begins. Radiation exposure is most strongly linked to leukemia, thyroid cancer, lung cancer. Nurses need to be aware of radiation exposure histories, especially in patients who've had multiple CT scans, radiation therapy, or lived near nuclear incidents. An NCLEX tip: always assess for cumulative exposure when considering patient history. Radiation can also affect reproductive cells, sperm and eggs. If these cells are damaged, they can pass mutations to future generations. In lab animals, scientists have seen radiation-induced birth defects and genetic disorders. In humans, we haven't found conclusive evidence of this from Hiroshima or Chernobyl survivors, but it's still a theoretical risk. So when patients ask, can radiation affect my future children? The most honest answer is, we don't know for sure, but the risk is likely low for medical-level exposures, and we take every precaution to minimize it. Let's talk about how we measure radiation. We have a few different units. Curie, CI, measures radioactive decay rate. 1 Curie equals 37 billion decay events per second. Röntgen, R, measures how much radiation ionizes air. REM. Let's talk about how we measure radiation. We have a few different units. Curie, CI, measures radioactive decay rate. 1 Curie equals 37 billion decay events per second. Röntgen, R, measures how much radiation ionizes air. REM, Röntgen equivalent man. This is the one you'll see most in healthcare. It factors in how damaging the radiation is to the human body. When patients get imaging or therapy, exposure is measured in millirems, mrem, or millisieverts, MSV. The higher the number, the more risk. For example, chest x-ray about 10 rem, CT scan hundreds of rem, radiation therapy much higher but targeted. On average, each person receives about 1/3 of a rem, 330 mrem, of radiation per year. Where does it come from? Radon from the ground equals the biggest natural source. Cosmic rays from space. Medical procedures like x-rays, mammograms, and CT scans. Food and water, which naturally contain small amounts of radioactive elements. So even if you've never had a scan, your body still receives background radiation daily. As nurses, we must understand this baseline exposure when evaluating how much extra radiation a patient has received. This helps us determine whether additional scans or treatments pose added risk. NCLEX style question. A patient asks if one CT scan is dangerous. What's the best response? Answer: one scan provides a relatively small dose, and the benefits usually outweigh the risks. We always try to minimize exposure. Now, let's discuss what happens when radiation exposure starts to affect the body in measurable ways. The first noticeable effect is usually a decrease in white blood cells, especially if the exposure is sudden and reaches around 20 rem or more. Why? Because white blood cells are made in bone marrow, which contains rapidly dividing cells. These are very sensitive to radiation. In practice, you may never see a patient with this level of exposure outside of radiation therapy or emergencies. But if you do, one of your first responsibilities as a nurse will be to monitor lab values, particularly the WBC count, and protect the patient from infection. You'll also be helping manage side effects like fatigue, nausea, or poor healing depending on the exposure level. Radiation isn't always harmful. In fact, we use it all the time to help patients. For example, technetium-99m is used in bone scans to detect fractures, arthritis, or cancer. Phosphorus-32 is used in some tumor imaging because cancer cells absorb it more than normal ones. Iodine-131 is used to diagnose and treat thyroid disorders because your thyroid naturally absorbs iodine. In these cases, the radiation is targeted, measured, and temporary. But patients may still ask, am I radioactive? The answer is often yes, a little, but only for a short time and not enough to be dangerous to others. As nurses, your role is to educate, monitor for side effects, and remind patients of short-term precautions like avoiding close contact with infants or pregnant women. Now let's talk about radiation therapy or radiotherapy. This is a treatment, not just a scan. It works by targeting a malignant tumor with a focused beam of gamma rays, often from sources like cobalt-60. To minimize damage to healthy tissue, the beam is usually rotated around the body, so the tumor gets a high dose from all angles, but healthy cells only get brief exposures. As a nurse, you may care for patients receiving external beam radiation or internal radiation implants, brachytherapy. Either way, you'll need to educate the patient on side effects like fatigue, skin irritation, or loss of appetite. Help with pain management and emotional support. Follow radiation safety guidelines, especially when implants are involved. Let's summarize what we've learned. We covered the discovery of radioactivity and the four major types. Alpha particles, big, slow, high ionizing, low penetrating. Beta particles, small, moderate ionizing and penetrating. Positrons, like beta particles but positively charged. Gamma rays, pure energy, low ionizing but highly penetrating. You now understand that radioactive isotopes are used to scan organs, treat cancer, and measure time in archaeological artifacts. And you've learned that we use tools like film badges, Geiger counters, and scintillation counters to detect and measure radiation. We also learned about half-life, the time it takes for half of a radioactive substance to decay. This concept is critical in medicine because it tells us how long a patient remains radioactive, how long an isotope stays active inside the body. We discussed fission, the process of splitting atoms to release energy, used in nuclear power and medicine, and fusion, the reaction that powers the sun. And we looked at the biological effects of radiation, from immediate cell death in high doses to increased cancer risk and potential but not confirmed genetic effects in low doses. Finally, you've seen that radiation is a powerful tool in healthcare, but only when used safely, with careful nursing support.